Hello class, this is Dr. Anderson and we are continuing our studies of the endocrine system, and this time we're talking about the thyroid gland. So here are our learning objectives, and first of all we need to talk about a little bit of anatomy. The thyroid gland has what's called a follicular structure. So there are little balls of cells, and inside the sphere of cells is this sort of jelly-like substance, and that's actually the thyroid hormone. And so we want to discuss how thyroid hormone is synthesized and how it's secreted. Now, when I use TH, I mean thyroid hormone. And there are two types of thyroid hormone. There's T3 and there's T4. So I'll either refer to them individually, and if I say thyroid hormone, then I'm talking about both of them. All right, so we're going to talk about the structure of the gland, how it makes and secretes thyroid hormone, and how that is regulated. So we've talked in general how the hypothalamus produces a releasing hormone that goes to the anterior pituitary, and then the anterior pituitary releases a stimulating hormone. We're going to follow that same pattern here. We're going to talk about what thyroid hormone does. We're going to talk about when you have too much or too little thyroid hormone. And then we're going to talk about a case study about a person that has something called Graves' disease. So this is a picture from a physiology anatomy and physiology textbook by Tutor and Grabowski. And so you see the thyroid gland is just below the thyroid cartilage of the larynx. So there's the thyroid cartilage, and then the gland is below that. It looks like a little bow tie. It's very, very vascular. And so two lobes on either side of the trachea. And in the follicles is a substance called colloid. So it's a great big protein that's turned into a jelly, surrounded by an epithelial layer. So if you're a vegetarian, you might not know what I'm talking about. But if you are a meat eater and you've made your roast or your roast chicken or something like that, and then you put it in the refrigerator, the protein in the juices form kind of like a jelly. That's a colloid. That's what you'd have in your thyroid gland. And that jelly substance, that colloid substance, is made of a protein called thyroglobulin. It's a huge protein that's basically little thyroid hormone. They're all linked up together. In between the follicles are some things called C cells, and these C cells produce a hormone called calcitonin, which, as the name implies, has something to do with calcium metabolism. All right, so here's thyroid woman, and here's the little bow tie thyroid gland in her neck right before the thyroid cartilage. And then it's blown up a little bit more. So then you see here's the thyroid gland made up of all these little follicles. And if we do, took a section of this and looked at it under a light microscope, here you see the follicles. So here are little epithelial cells. Here's an epithelial cell. Here's an epithelial cell. These are the guys making and secreting the thyroid hormone, and they're storing it in this big colloid called thyroglobulin. And essentially, it's lots and lots of T3 and T4 molecules all linked together covalently in this gigantic protein called thyroglobulin. So, thyroid hormone, as I said with our learning objectives, thyroid hormone is actually two hormones. One is called triiodothyronine, which is not easy to say. That's T3. And the other one is thyroxine, which is T4. Now, what you do is take an amino acid called tyrosine, and you make a dimer of it, and then you iodinate it. So it's important to have iodide on hand for the synthesis of thyroid hormone. And many of you may realize that when you buy salt in the grocery store, it's iodinated. So table salt is a source of iodide, so we can make thyroid hormone. People that don't have access to that can sometimes have difficulty making thyroid hormone because they can't iodinate it. And in those follicular cells, we're going to have secondary active transport of iodide. So if you remember from some of Dr. Olson's lectures, you could have a cell, you'd have a sodium-potassium ATPase on one side, that's a primary active transporter making a sodium gradient, and then we could use the sodium gradient to bring in iodide along with the sodium. And so that would be secondary active transport. The rough endoplasmic reticulum and the Golgi apparatus help synthesize this thyroid globulin, and then it's stored in the colloid. Alrighty, so here's our cell. Look right here. There's that secondary active transporter for iodide and sodium, and so the implication is there's a pump on the other side of the cell. So this is a way to get iodide into the cell so it can make thyroid hormone. So you see this is a tyrosine molecule. So you see the ring and the hydroxyl group. So here we see two iodinated groups on a thyroxine, and here we just see one. You put both of those together, and if we have 3 iodides, then it's T3. And if we have 4 iodides, then it's T4. So then all of this colloid is stored out here, and this is the gigantic thyroglobulin, and so that's the synthesis process. And then when you want to break it down, there are enzymes that break it down. You put it in a little vesicle. The vesicle then merges with the lysosomes. You chop up these little bonds, and now you've got lipid-soluble hormone that can simply diffuse out of the cell. It's going to go out here in the plasma and find thyroid-binding globulin. Because remember, if this is lipid-soluble, it needs a protein carrier. So once you have the synthesis of thyroid hormone in the form of thyroglobulin, then you can engulf little pieces of thyroglobulin in a vesicle, fuse it with the lysosomes, break free basically the T3 and T4, and then it can diffuse out of the cell. All right. T3 and T4 are lipid soluble, and that happens because of the iodination. It has to be carried in the blood by protein. So thyroid binding globulin is one. Transthyretin is another protein that carries it. And remember, albumin, all-purpose carrier. Because it's carried in the bound form, that extends its half-life. The half-life of T3 is 24 hours. The half-life of T4 is 1 week, and therefore we know T4 is more lipid-soluble than T3. There we go. So how does thyroid hormone work? Well, T4 is more abundant, but T3 is more potent. It's an interesting kind of thing. So evidently, there's more T4 released, and then there are enzymes out in the periphery that take off one of the iodide groups, and now you have T3, and T3 evidently is the thing that goes into the cells and does the job. So you deiodinate T4, it becomes T3, T3 then binds to the thyroid hormone receptor. That's the bulk of the evidence points to that mechanism. Now, remember, we can have lots of categories of hormones, but for this purpose, I said we've got our proteins, our water-soluble hormones, and then we've got our steroids and thyroid hormone as our lipid-soluble hormones. So thyroid hormone, something happened here. So thyroid hormone works like the steroid hormones. It goes into the cell. It's going to bind to nuclear receptors, and there are receptors for thyroid hormone in just about every cell of your body. Thyroid hormone and its nuclear receptor together act like a transcription factor. They bind to hormone-sensitive regions on the DNA that guides RNA polymerase to or away from the promoter. In the case of thyroid hormone, typically it's increasing transcription. You transcribe a gene, and then you're going to make a protein. All right, so how is thyroid hormone regulated? Well, we start with the hypothalamus. The hypothalamus produces a releasing hormone. It's a peptide, thyroid releasing hormone, and it goes through the portal system. So it doesn't have to go through the heart to get to the anterior pituitary. It binds to receptors on cells in the anterior pituitary, and those cells produce thyroid stimulating hormone, or TSH. TSH is released into the venous blood. It's carried to the right heart, through the lungs, to the left heart, out through the body, and then it's going to find receptors on the thyroid gland. TSH is the signal for a number of things. TSH tells the thyroid gland to uptake iodide. TSH tells the thyroid gland to make more thyroglobulin. And TSH tells the thyroid gland to break down thyroglobulin and release thyroid hormone. And thyroid hormone affects most cells of the body. So now we release T3 and T4. T3 and T4 go out and have peripheral effects, but we want to make sure that thyroid hormone levels are not too high. And so when T3 and T4 increase, they feed back to inhibit, so this is an inhibitory sign, to inhibit the anterior pituitary and to inhibit the hypothalamus. So we have mechanisms that turn on thyroid hormone when we're cold, when our metabolism is low. That drives thyroid hormone synthesis, and when thyroid hormone levels are high enough or in danger of getting too high, then we have a way to turn the system off by negative feedback. So what does thyroid hormone do? Well, it transcribes things. So in the presence of thyroid hormone, and remember we think it's T3 that's really doing the work, you have an increased transcription of what I would call energy-intensive proteins. And a very, very energy-intensive proteins would be the sodium, potassium ATPase. We're also going to upregulate glycolytic proteins, Krebs cycle proteins. So you're making more ATP and you're burning up more ATP. That increases your metabolism. You also make more growth hormone. Growth hormone promotes protein synthesis and growth, which increases your metabolism. And when you increase your metabolism, every time you have chemical reactions and you're breaking bonds, you are releasing heat. We have to follow the laws of thermodynamics, which say there is no such thing as a perfect energy conversion. So when you break down a glucose molecule to make ATP, some of that is lost as heat. And when you break down an ATP molecule to pump an ion, some of that energy is lost as heat. So you increase heat production, which we call a caloriogenic effect. Thyroid hormone is also essential to the fetus and to babies because it's very, very important for the growth and development of the nervous system. So it transcribes all kinds of proteins that tell the neurons where they're supposed to be growing, to tell the little synapses where to link up, to tell the neurons where to myelinate. And so actually it's a very sad thing if you have a baby that does not have thyroid hormone and it's not caught. There's all kinds of important brain growth that's happening in the first 2 years. And if the child misses out on that, the child has mental retardation and you can't get those years back. So in Minnesota, infants are tested for thyroid deficiencies. And I'm all in favor of testing for something like that because you can do something about it. It's hard when you test for a disease and then there's no cure for it, but if you can test something that you can actually give the child thyroid hormones so they can develop in a healthy way, to me that's just a really great thing. All right, so thyroid is permissive. It upregulates beta receptors, which means we're more sensitive to sympathetic stimulation. That increases the heart rate, increases the stroke volume, which is the amount of blood that's pumped out on a squeeze. It increases lipolysis. It increases GI function, and it increases the excitability of the central nervous system. So it has metabolic enhancing effects. All right. What happens if you have too much thyroid hormone? All right. Thyroid hormone is your metabolism hormone. So you would have a very high metabolism. And you'd have a high appetite, and you could eat a lot of food, and you might even lose weight. Your metabolism is so high. Because your metabolism is high, you're producing all kinds of heat, and the person's heat intolerant. They want to walk around in shorts when everybody else has their long sleeve shirts and sweatpants on. Because it enhances cardiac function and increases the sensitivity of the central nervous system and the sympathetic nervous system, we could have heart dysrhythmias, heart palpitations. Person could have hypertension. This is a little bit, this could happen or not. We're going to increase the activity of the sympathetics and increase the tension of blood vessels. However, if we're venting a lot of heat, the blood pressure might not go up. And that's all I'll say about it right now. When we get to the cardiovascular system, you'll have another layer of understanding of what I mean here. And maybe I'll remind you that we talked about this. People who have hyperthyroidism can be emotionally volatile. I mean, they're just jazzed because of all this increased central nervous system excitability. They can't sleep. They can't settle down. So they're so tired. And because there's an enhanced GI function, they can have diarrhea. What's the flip side? What if you have hypothyroidism? Well, you have a low metabolism and you don't feel like eating, and yet you're gaining weight. And if that's not unfair, I don't know what is. You can't generate metabolism, so you feel cold all the time. There's an interesting set of symptoms that people with hypothyroidism have that's collectively called myxedema. What happens is there's a disruption or a abnormality in extracellular matrix molecules. You produce a lot of molecules that are called glycosaminoglycans, or GAGs. We used to call them mucopolysaccharides. And these are really big, fluffy molecules with lots of negative charges. And so a lot of these molecules accumulate. They accumulate under the skin. The skin gets dried and kind of puffy. They can accumulate in the heart and affect heart function. They can accumulate in the larynx and affect how the voice sounds. They can just do a lot. People lose their hair. It's not a fun collection of symptoms, and mostly in the skin. Hyporeflexia. You tap the knee and it hardly moves because there's a low activity in the central nervous system. I don't have it here, but that implies that people with hyperthyroidism would have hyperreflexia. People with hypothyroidism are going to feel lethargic and depressed. How is that different from fatigue? The people with hyperthyroidism can't sleep, can't settle down. They're just going, and they're just exhausted. The people with hypothyroidism just can't wake up. They just can't get it off the couch. They feel slow and depressed. In fact, depression is a differential diagnosis for hypothyroidism. And constipation. So I have known people that have had thyroid cancer and have had to have their thyroid gland removed. And when they get their checkups to make sure they're cancer-free, they have to stop taking their synthetic thyroid hormone medicine. And they tell me that the worst symptom to deal with while you're getting your testing done is the constipation, because the GI tract just slows down. All right, so we are doing a presentation, so of course we have time. And I'm going to talk about a case study from your textbook. It's from chapter 19. So we have a woman, and she's very nervous. And she has heart palpitations. She's heat intolerant. She has weight loss and increased appetite. So she goes to her physician or her nurse practitioner, and here's what's going on. She's 23 years old. And for the last year, she's gotten more and more nervous and irritable, and she's experiencing something called heart palpitations. It means she can feel her heart beating or feel her heart skipping beats. She's actually aware of what's going on with her heart, and it distresses her. Her skin is warm and moist. Her skin actually looks beautiful, but she's so hot. She just feels hot all the time. She's lost 30 pounds over the last year. Besides, but she's ravenously hungry and eating all the time, and yet she's lost 30 pounds. She's been a very active person, but she actually has muscle weakness and just is not able to jog like she used to. Her menstrual periods have been affected, and she's having an interesting symptom. She has double vision when she looks to the side. Not with if she closes one of her eyes, but when she looks with both eyes, there are occasions when she has double vision. What in the heck is going on here? So she's examined. She's 5'7", and she weighs 110 pounds. That means her BMI is 17.2, and that is low. So she's very, very thin. Her blood pressure is 140/60. Now, we have not gotten to the cardiovascular system, but for somebody like this, I would expect her blood pressure to be, say, 115/60. Whoops, sorry about the 60. So her diastolic isn't bad, but that systolic pressure is way too high. I suspect she has high blood pressure when her heart is pumping, but her pressure seems kind of normal when her heart is not pumping, the diastolic pressure. And I bet that's because she's trying to vent all that heat. Her pulse is 100 beats per minute. Now, a pulse of 100 can be normal for some people. But, you know, if she's been a jogger, I would bet her pulse should be something like 60 or 70. This pulse seems way too high. Her respiratory rate is 17 breaths per minute. I would expect her respiratory rate to be more like 10 or 12. Now, here's something interesting. She has exophthalmos. That means her eyeballs are bulging out of her eye sockets. And this is something can happen when the eye muscles are weak and when you have a lot of swelling behind the eyeball. In addition, she has the double vision. Here's something interesting. The lower front of her neck is swollen and she has hyperreflexia. So that tells me that her central nervous system is really, really excitable. So here's her eyes. You can see a lot of the white of her eyes because her eyes are kind of pushing out. That's that exophthalmos. And look, the front of her throat is sticking out, and this is something called a goiter. All right. So are these signs and symptoms within the normal range? If not, are they too high or too low? And as we've gone through, her BMI is too low. Her blood pressure is too high. Her pulse is too high. Her respiratory rate is too high. This is not a healthy sign. This is not a healthy sign. Her neck is swollen and her reflexes are too brisk. Now, we have some laboratory results. Her sodium appears to be normal. Her potassium level is on the high side of normal. Her chloride is normal. Her pH is normal. Her calcium is normal. Okay. Her parathyroid hormone is normal. Her glucose is normal. Her prolactin is normal. Now, why are we studying prolactin? Well, we're trying to say something about her anterior pituitary, and remember, she hasn't been having periods. Her mid-cycle estrogen is on the low side. And her T4 is high, and that's her total T4. Remember, some of it's bound. Her free T4 is high, and her thyroid stimulating hormone is low. You see that? So remember, TRH goes to the anterior pituitary, and we get TSH. And then that goes to the thyroid gland, and we get T3 and T4. Now, it used to be when you did a plasma test, you just did TSH and T4 because that's what insurance would pay for, and that's what could be done. Technology has increased that we can get all these values. But can you see what's going on? Because T4 is high, it's feeding back and inhibiting TSH. I assume T3 is high too. I don't know that from her values, but I assume that, and I assume that TRH is low as well. I don't know that, but it would make sense given the other things we're seeing. All right, so her electrolytes are normal, her parathyroid hormone is normal, her fasting glucose is normal, her prolactin was within normal ranges. I got to go back and look at this. 100. Estrogen is on the low side. Free T4, total T4 is higher than normal. TSH is lower than normal. And we talked about how this high T4 is feeding back and inhibiting the anterior pituitary so that TSH is lower than normal. So we've talked about how the feedback has been altered in this woman, but what do you think's going on? Can you see that she has hyperthyroidism? The evidence, what's the evidence for the diagnosis? And I want you to think about this. We'll talk about this in class, but we know her T4 is high, but think about her other symptoms and think about why her other symptoms are consistent with hyperthyroidism.